In 7.3, we're asked to find the period and frequency of small vibrations of this system. These bars are all the same length and all the same mass. They're 2 kilograms each. And one of the key words in this question is small. We're looking for small or oscillations, really, of this system. We're looking at the natural frequency. So if I draw a little sketch, that's the vertical, and this is some perturbation away from that. So and this is theta. And theta is small, and that means that we can use, and we'll use this later, our small angle approximation. So a small angle approximation that we're going to use is that cos theta is approximately equal to 1 minus theta squared over 2. Okay, so we're going to start by noting that there are only conservative forces are acting, so we can analyse this system with potential energy plus the kinetic energy is equal to a constant, and we're going to just add up our various components of potential energy and kinetic energy. So I'm going to label the bars 1, 2 and 3. Bars 1 and 2 are in a fixed axis rotation around this point, whereas bar 3 is in translation. There's no rotation, it sort of goes like that, whereas bars 1 and 2 do that. So the whole thing swings outwards. So, like so. So let's firstly work out what the potential energy of bar 1 is. And to do that, we'll need to work out what the elevation of the centre of mass is. Now each bar has a length L, and so the centre of mass is going to be L over 2 along, assuming that they're a constant density and uniform. So those are the positions of the centre of masses. So that length there, that is L over 2. So the elevation of the centre of mass of 1, and I'll call it H1, the elevation above its equilibrium position, and this is just a bit of trigonometry, is L over 2 minus L over 2 cos theta. And I can just reassure you, if I do it, that that's the case by doing a little close-up. So that's the centre of mass. This is the distance L over 2. This is theta. And that's its initial position. So this length here is L over 2 times cos theta. And this distance here is L over 2. So that distance there, which is the elevation, is L over 2 minus L over 2 cos theta, which is what we've got here. So, with that, we can write down that the potential energy of 1 is the mass, m, g, times, well, before I go any further, I'm going to substitute in my small angle approximation, and that makes it nice and simple. You get L over 2 times theta squared over 2 once you make that substitution. So that gives us L theta squared over 4. Now we can do exactly the same thing for link 2. Potential energy of link 2 is identical. Now the potential energy of link 3 is calculated in the same way, but now we need to find the elevation of, it's going to be the same as this point, so therefore the centre of mass will be elevated the same as this point is elevated, we can do exactly the same trigonometry, except now rather than L over 2, we consider the whole length, such that simply the elevation of 3 is equal to L theta squared over 2. So our potential energy is mg L theta squared over 2. And our total potential energy, which we'll need later, which is a sum V1 plus V2 plus V3, is equal to mg L theta squared. So nice and simple. So that's evaluating the potential energy. Now we can evaluate the kinetic energy. So the kinetic energy of a rotating bar in fixed axis rotation around this point is half I, where I is the moment of inertia of the bar around its endpoint, times theta dot squared, where theta dot is the angular velocity. So I, which wasn't given in the question and would be given if you were, if this were an exam question, because we don't expect you to remember these off the top of your head, is a third of the mass of the bar times L squared, and that's theta dot squared. So that's 1 over 6 m L squared theta dot squared. And the kinetic energy of this one is exactly the same, m L squared theta dot squared. So now the only thing we need to calculate left is the kinetic energy of bar 3, and the speed of the centre of mass of bar 3 is going to be equal to the angular velocity of this link multiplied by its length. It's the tangential velocity. So the speed, let's write it here, is equal to theta dot times L. So now we can just use our standard expression for kinetic energy, half m v squared equals half m. Now we make that substitution, theta dot squared L squared. So our total kinetic energy is T1 plus T2 plus T3. We're adding that to that to that, and that gives us 5 over 6 m theta dot squared L squared. Okay, so we are almost there. We've now got to add our potential energy to our kinetic energy, and I'm going to do that. So we've got mg L theta squared plus the kinetic energy, which is 5 over 6 m theta dot squared L squared, which is this, is a constant. Now I'm going to differentiate that with respect to time. What I'm going to get is 2 mg L theta dot theta plus 5 over 3 m theta double dot theta dot L squared equals 0. Now I can divide through by theta dot, and we'll get a governing equation which looks like this: theta double dot 5 over 6. Also the m's look like they divide through as well. 5 over 6 times L squared plus G L theta equals 0, and I can divide through by L as well there to leave us with 5 over G L theta double dot plus g theta. And that's our Gaussian equation. And if we go to our lecture notes, we can recognise that it's in this form. And so that means our angular frequency, our natural frequency of oscillation, is the square root of this term divided by this term. So that's g times 6 over 5L. And I've lost m somewhere. No, I think that's okay. So that's the square root of 6 times 9.81 over 5 times, I think the lengths of the links are 1 meter. So that gives us a angular frequency of 3.43 radians per second. And if we want that in hertz, we divide it by 2 pi. And 1 over that gives us the period. So period equals 1.83 seconds. So there we go. We established in the end that the frequency didn't depend on mass, and I was a bit surprised about that to begin with. But if you remember that a pendulum's frequency isn't affected by mass, and essentially this is just a pendulum, so that all makes sense. Okay.